Our next presenter is Sunbin Song from the National Institute of Neurological Disorders and Stroke. She's a senior researcher with the National Institute of Neurological Disorders and Stroke, and you can find her complete biography in your briefing book. Sunbin is going to present a VR study, VR to study motor learning. Sunbin?
Thank you very much. This is quicker. I have a lot of slides, and I promised I would get through them in 8 minutes. So I'm going to breeze through some of the technical details, and you can ask me more later about them, but hopefully it'll be pretty clear. So today I'm going to talk about the future of motor skill training using interactive and immersive virtual reality and some of the work we've done at INDS. So what are some of these applications? Some of the applications are in sport and simulation and training, and of course rehabilitation after brain injury, such as after stroke or traumatic brain injury, which is why we're quite interested in it. Now, if we have a science fiction view of what the future of this might look like, you can imagine playing tennis with an AI Roger Federer at home using just commercial hardware. And you can sort of extrapolate and, replace AI Federer with a real Federer or a real rehab therapist or another patient, or you could have guided training. In general, you can just imagine all the variants of this and how useful it will be, how it will change the future of rehabilitation. Okay, and what about right now is so important to make this future feasible? The first is that a real-life task can be of daily living, can be mimicked by interactive immersive VR. There has been a lot of work with what we call non-immersive VR, which you could argue is not VR at all, using things such as the Nintendo Wii or Kinect-based games. And they use them as an add-on therapy, and they've generally failed multi-center clinical trials to improve patient outcomes. Could be because game learning does not generalize to real-life activities. The second thing about immersive VR is that it's cheap, getting cheaper, and can be home-based. And so immersive VR systems like the Cave systems, for example, or devices or robots, they've done better than a non-immersive VR to improve outcomes, but they're not easily home-based and they're quite expensive. And so we have a real opportunity right now. Okay, so how do we currently study motor learning? So we use a lot of motor sequencing tasks, such as this serial response time task. I'll be talking a little bit about it, where you have these button pushes and you press key press in response to a stimulus that appears on the screen. Why do we care about the old way of doing things when we have VR, when we have all these immersive VR systems? Well, we care because it's been really well characterized for more than 40 years. Here's an early study I did in my PhD, and at that time we were using probabilistic sequences. You can embed very complex regularities in them. For example, you could even go up to 6 order, where you have to integrate across 7 events, and humans can learn this after a long training. And you can differentiate between sort of this general motor, visual motor binding and sequential learning of these very complex regularities. The other thing we know is that we've characterized the practice-dependent and sleep consolidation stages and components of motor skill using tasks such as this. This is a study I did at NINS. And learning's not over as soon as training is over. It continues as you sleep, as time passes, and it goes into the retention stages. And these are all very important if you're thinking about the long-term outcomes of a patient. Okay, and lastly, we know the neurocorrelates. These are 2 studies I did at NINS. First, looking at intra-individual variability and what that correlates with. It correlates with functional connectivity to the left dorsal premotor cortex and other motor areas of the brain. And we've also looked at inter-individual variability, which is much larger than intra-individual variability, and it correlates with structural features of the brain, such as the structural white matter integrity of the sensory-motor cortical striatal tract. And so you have all this that's known based on these very simple tasks. So when you're constructing a VR task, you don't necessarily want to go straight into VR tennis. You want to do something that can connect to the prior literature so you can make a bridge. And so that's what we did. This is our virtual reality SRTT task. I'm just going to play the video. This is a mixed reality green screen video that we made. I'm real, my hands are real, but the room is all virtual, the table's virtual, the balls are virtual, and the ball pops up. I'm just putting it in different pockets. See at the top, I say version 1.0.5. We have several versions of this. Two of these that we tested. I'm not going to go into all the details of the versioning today, but for example, in this version, people with color blindness had an issue, so we changed it to color-blind proof colors and things of this sort. In this, you can see the trajectories just for demo purposes. The subjects don't actually see these trajectories, but this is to show you the kind of information we can collect. We can collect the movement trajectories to the pocket and also back again. I'm going very slow intentionally for demo purposes, but we tell people to go as fast as they can while being accurate. Okay, and unbeknownst to them, there's complex irregularities embedded in the order of these balls. The other thing, we're also tracking head movement. Okay? And in our study, we actually, first pass, we had them sort 1,000 balls during trainings, separated into 10 blocks, and then 500 balls during test. We generally try to test as long as possible, for these studies. In our next round, we're probably going to test them even longer and across several days. This is our first round of this study. Okay, this is another video showing you the kind of output we get. For example, these are the 4 colors we ended up using colorblind proof. But you can see that we can track very well the trajectories going to the balls and also the head movements, and we can see it in 3 dimensions. This is very novel. This has not been done in our field. Number one, they're unconstrained. There's no robot. There's no manipulandum. They can do whatever they want as they would in a natural setting. Okay, and you can collect very detailed data. It's not moving forward. Up this way? Okay. Oops. Too much. Okay. It's working so well before. This way? Okay. Okay, so in our experiments, we're still working on the different versions. We had version 1.0.0, version 1.1.0. I'm not going to go into too much detail, but the important part here is that all our versions, the virtual reality version is judged as much more engaging than the button pushing version, even though we're having them do it for 1,500 balls, same as key pressing. It's not as fun as a fun game like this VR Funhouse. That was a game from NVIDIA. We used it sort of as a gold standard in terms of immersiveness and naturalness, as it was the best game on the market, made by the graphics card makers. And our game was comparable in immersiveness and naturalness and movement to that, so we were quite happy about that. And this is quite important for rehabilitation because you want subjects to use it, and it has to be engaging for that purpose. We can gamify it more, make it more engaging, but that's for future versions. Okay. And this is what, for example, data from a traditional SRTT with the key presses look like. We use the interleave training. Some of you from the rehab world may know that optimizes motor skill learning. And we have these test sessions where we have complex regularities embedded in it. I won't go into too much detail about it, but we have second up to third, up to fourth, and then fourth and higher order regularities. And as you train people, they learn these regularities more and more, as you can see with faster response times. And we measure those differentials. And on the right, you can see sequence-specific response times. Okay. Okay, with the VR SRTT, you get very similar results with our version 1.1.0. These are all preliminary. We're still testing, so I'm going to go to the next slide. And because this is what's really great about VR, is that you can get a lot more information than just the response times. The response times will be from when the stimulus appears to when they make the response. But if you look at the velocity profile, you can actually separate into two stages. One's the onset time and one's the movement time. And you can look at the time of peak velocity, which in trajectory and reaching and pointing tasks has been a very classic measure of motor skill learning. And you can do that with our VR data. Okay, and if you look at the onset time of peak velocity, and the movement time of peak velocity, you can see that there's a kind of a decrease with training, and that there's sequence specificity for the movement time of peak velocity. You can also look at the variance. I'm struggling with this. There we go. You can look at the variance, and you can also see a decrease in variance. And for movement time, it seems to actually increase for the low frequency transitions, and not increase for the pattern high frequency transitions. And overall, not to get too detailed about it, but overall what that's telling you is that people are learning how to respond to these virtual objects as if they're real life objects. And you're also able to embed very complex regularities into the ordering of these virtual objects in a way you never could with a real life object. And you can show learning, they're becoming less variable, they're becoming faster, their time of peak velocity is shifting, just as they would in a real life task. But you're able to do this in a virtual environment. And so that's very, very promising. It suggests that the future that we envision is very close. And of course, the other thing is that we're going to integrate more and more in our analytics a lot of the data that we're collecting, such as head movement data, head direction data, hand rotation. We can also integrate glove-based hand tracking, eye tracking. That's what we're currently working on. Our next version is going to be the tennis version, so it gets closer and closer to something that can be, the Roger Federer versus us kind of future. And we're also creating MRI-compatible versions of these tasks to look at their correlates. Okay, and what's this useful for? It could be very useful for diagnostics, not just research. So I think did I go over time a little? Maybe a little bit. I went over time, but these are some. I want to acknowledge my colleagues here. Thank you.
Thank you, Sunbin. This is a really interesting area of research. We have a few minutes for questions from the audience. Anyone have any questions for Sunbin? Yes.
Darlene Curley from the Jonas Fund, and I'm very interested in the rehab and the diagnostic aspects of this. And what suggestions do you have for encouraging healthcare students pursuing doctoral work to go into this area of research?
I think they should. I think it is the future. Well, there are already companies trying to market virtual reality, physical therapy. I think there's a gap still. It's not getting number one, virtual reality is not getting adopted very fast, and it's usually by gamers. There's a couple reasons why. You have like eye strain, simulation sickness. I think all of these things will improve with the tech sector moving ahead, trying to solve these problems. Also, the price points are getting lower and lower. Right now, they might be a little bit still too high. So that's one area in which there's a gap. But the second area in which there's a gap is the gap that we're trying to fill, which is a gap in knowledge. And that gap in knowledge, as virtual reality is used more and more, it's going to shrink incredibly fast because of the huge amounts of data that's generated by these virtual reality platforms. You can see just from one subject in the 500 trajectories, I mean, just how much data you might get from an hour or 2 hours of training of 10,000, patients. And so probably machine learning, deep learning, some of these algorithms, those are going to be developed, and people are going to be able to individualize to each subject, diagnose, have targeted therapies. These are things that right now you kind of rely on the intuition or skill of your physical therapist. It's more of an art than a science at the moment. I think it's going to become more and more of a science. And so that I would suggest anyone going into it that they look more and more into sort of what is going to happen is it's going to become more and more automated.
Any other questions? Well, Sunbin, I'm a little bit interested in the MRI application and how you're doing that with virtual reality and MRIs. Are you using a functional MRI? Can you talk just briefly about how you're doing some of that research?
So at the NIH, in our lab, we use two imaging modalities. One is MEG magnetoencephalography, and one is MRI magnetoencephalography. Has better temporal resolution, kind of like on par with EEG, and very good spatial resolution. fMRI has, very, very good spatial resolution. And they each have their different challenges. Some of the challenges that you can't bring anything that's ferromagnetic into the MRI scanner. And so we're working on using hand tracking with sort of these deep learning algorithms in the scanner. So that's one way to solve that problem. That's our main way. There's also some infrared depth sensing technologies that have been developed that we're also integrating into sort of some of our tests to make them compatible with the MR and MEG scanners. And right now, this is something that's been sort of one of the missions of the NIH that has been a partial failure, which is to come up with an objective diagnostic that is based on a brain scan for some conditions. For stroke, it's worked very well. You can look at the perfusion-weighted image and find the penumbra and the core and stuff like this. Anything you have a brain lesion, but for example, TBI, a lot of times that's image negative. There's nothing on the MRI that can be used to diagnose TBI per se. You have to wait sometimes for them to die, and then you do an autopsy and stuff like this. It's better to know that and while they're alive and to use that to treat them. They're the same with mental illness, same with a lot of these conditions today. There's not really a brain scan that can be used as a diagnostic. In the future, you can imagine maybe you use a task that is really realistic to what their deficit is, and try to use that to along with a MR to create a diagnostic. It could happen.
Thank you very much, Sunbin.